problem 26 states, prove that if n is greater than 1, the nth partial sum of the harmonic series is not an integer. And remember, the harmonic series, that is just 1 over I. Oh, I mean 1 over n. That's just 1 over n. The summation 1 over n like that, where this is a p series where p equals to 1. Like that. Just remember that. And then we're given a hint here, and it's the hint is bigger than the equation. So hint, let 2 to the power of k be the largest power of 2 that is less than or equal to n. In other words, what this means is if n equals to, for example, 7, let's say n equals 7. So for n equals 7, we have 2 to the largest power is going to be 2 to the 2 equals to 4. So it's the largest power of 2 that is less than or equal to n. So you can't go 2 to the 3 because that equals to 8, and that's greater than 7. So we can't do that. Just to give an example there. And then let m, capital M, be the product of all odd integers that are less than or equal to n. So in other words, if n equals to 7, then the m is going to be equal to 1 times 3 times 5 times 7. And yes, that's what we get. Alright, and then suppose that s sub n, which is the nth partial sum of the harmonic series, equals to m, an integer. Yeah, so if the nth partial sum is equal to an integer, so just suppose that, and we're going to prove that it's not. But first, if you do assume it is equal to an integer, then this number right here, capital M, which is over here, times it by 2 to the power of k times the Sn equals to m times 2 to the power of k times m, and the right side of this equation is even, and we'll show that soon. And then we're asked to prove that the left side is odd by showing each of its terms as an even integer, except for the last one. So basically they're saying this is even, this is e, and then they're saying show that this is equal to odd number. So then that means this is not this equality is fake. Hence this supposition is wrong. So then the nth partial sum is not an integer. So that's the idea. Alright, so now let's take a look at the solution. And again, we got to prove that this nth partial sum of the harmonic series is not an integer. So solution, the nth partial sum of the harmonic series, where again it's a p series with p equals 1, is, and we can write this as s sub n, so just a summation of, and we're going to go all the way up to n, so I'm going to do summation, if it's called Sn, summation up to n, so we're summing it up to n, not infinity, up to n, starting from, I'm going to call this I equals 1, and this is going to be 1 over I. Alright, so here is the nth partial sum. So now we are asked to prove that for n is greater than 1, so n is greater than 1 here, that the partial sum is not an integer, so the nth partial sum. That is not a whole number such as -1, 0, 4, 99, but in our case, since all the numbers are positive, we don't even need to deal with any negatives like that. So it's just basically a whole number, such as 4, 99, etc. Now let's follow the hint given. So let 2 to the power of k be the largest power of 2 that is less than or equal to n. Let capital M be the product of all the odd positive integers that are less than or equal to n. And suppose that Sn, an integer, then, so we're just following this exact same hint. Now we're going to write this over here. M to the power of 2k Sn equals to m to the power of 2k m. So m times 2 to the power of k Sn equals to m 2k m. Alright, so let's take a look at this hint that we're given, so this equation. So for n is greater than 1, so that's what we're asked to find, the right side of the above equation is an even, not and even, is an even integer. Alright, and we can see this because, well, if n is greater than 1, then, well, that means n is greater than or equal to 2. Yeah, so it's going to be 2 is the smallest. It can be. Yeah, then what we have is, well, 2k is the largest integer less than or equal to n. So if it's 2, then this equals to, well, it's going to be greater than or equal to 2 to the 1. Yeah, so that's the largest it can be, and yeah, so, well, in other words, it's going to be greater than 2 there, if n is greater than or equal to 2. In other words, we have k is greater than or equal to 1, so there's the k there. Yeah, yeah, so that's what we have is m times, I'll just put if that, thus, m times 2ks, or we're only doing the right side, m times 2 to the k times m. Then we have a scenario such as, well, let's look at the first case. Well, first we know that lowercase m, it's an integer. This could be even or odd, doesn't matter. This could be even or odd. Yeah, even or odd. And this one right here is actually odd, but it doesn't matter what it is. And that's odd because we're only looking at the odd numbers. For example, 1 times 3 times 5, this equals to, well, 15. So odd times odd is always odd. So anyway, so that's what we have there. And then this right here is, well, this is going to be 2 to the 1, or 2 to the 2, or 2 to the 3, etc. These are all even. So these are all even. And whenever you have any number times an even number, any number or any integer, yeah, so it's all integer. Any number that's an integer times it by even equals even. I.e., if you had 11, that's an odd, times by 2 equals to 22. Or if you could have 13 times it by 3, or times it by, let's go to 4. This equals 2, well, 2 carry the 1, 4 times 1 is 4, then add 1, 52, like that. Yeah, so it's always always an even number, because, well, again, it's a factor of 2. Alright, this is an example. So that means this is, you're multiplying by an even number. This could be even or odd, doesn't matter. And this could be odd, this is odd, even if it's even, doesn't matter, because this is even. Thus, this right here is equals to an even number. So this is always even. And whenever you're having all integers, these are all integers, multiplied by each other, you're just gonna get an integer. So yeah, so just leave it as that. So it's even integer. So now we will show that the left side of the equation, this right here, with the partial sum instead of just writing m, this is an odd integer. And yeah, so we will show that the left side of the equation is an odd integer, contradicting the equality, and thus showing that the supposition that Sn is an integer must have been wrong. So if this is not even, then these aren't equal. In other words, it's not an integer. So if we take a look at the left side, that's m times 2 to the power of k times Sn. So let's write that in. So m times 2 to the power of k Sn, and now this equals 2, and we know what Sn is. Sn is all the way above here. So this Sn equals the summation from I equals 1 up to n of 1 divided by I. In other words, that's the partial sum of the harmonic series. So this equals m times 2k. Now let's make this better, m. Alright, and this can be times it by the summation up to, not infinity, I'm too used to writing infinity a million times, n, and then this I equals 1 over I. And now what we'll do is I'll just move those inside. I'm just going to move this inside the summation there. Again, we could factor that in. It doesn't change anything. Just make it neater. So this is going to be up to n, I equals 1, then m 2k over I. Alright, so multiply that inside like that. Alright, so now that we have this, now let's consider the scenario where I is greater than or equal to 1, but less than or equal to n, and I is odd. So we're basically looking at when I is odd. So I is odd, and it sits between there. Then capital M divided by I is an odd integer, since I is one of the odd integers that were multiplied together to form capital M. In other words, m over I is equal to, well, for example, 1 times 3 times 5, if m goes all the way up to 7, and then times by ... all the way to I. And yeah, this m, it can keep going on, times by ... all the way until whatever number it gets, that's going to be less than or equal to n. So in this case, if I is odd, well, this is going to cancel, because it's part of that m. And this whole thing is still going to be odd. So it's still going to be odd, and it doesn't change anything, so it's still odd there. Or I'll just be like still odd. still odd, and thus what we have is nothing changes. Summation from I equals 1 of m over I, or 2k, m2k over I. This is, well, going to be odd. This is going to be odd times even, a summation of them all. And actually, yeah, this is important to be careful. We're not summing that all up. We're just considering the case where I is odd, because I is going to go from odd, even, whenever you go in 1, 2, 3, 4, because you're incrementing it. So we're only going to consider the m over m2k over I terms that are odd, where I is odd. And then this is going to be, well, it's going to be an odd times by 2k is even. So then odd times even, this is going to still be even. So then these terms are going to be even. Alright, so now that we have this is even when I is odd. Now the next scenario is when I is even. And again, I is between, is greater than or equal to 1 and less than or equal to n. Basically all the terms in the summation there. Then we can write I equals to 2 to the power of r times L, where 2 to the power of r is the largest power dividing I, and thus L is an odd integer. This is because dividing by the largest power of 2 removes all even factors. And basically, well, for example, just to illustrate this, for example, if we take I is equal to, so I'll write, for example, if I is equal to 10, then the highest factor is, well, this is going to be 2. If this equals a 2RL, then the highest factor is, well, 10 divided by 2. You can't 10 divided by 2 to the power of 1. You can't divide this by 4 because that'll be 2.5, and that's not a whole integer number. So then this is going to be like that. This equals to 5. So in other words, this equals to, well, 2 to the power of 1. So 2 where r is the highest power. So 2 to the power of 1, the highest power dividing I, which is 10, times by 5. And again, this is odd. So you're always, because you're taking out all of the factors of 2 out of there. That's pretty much what that means. And let's do another example. If I is equal to 20, so if I is equal to 20 here, then the highest power, you're going to divide by 2 to the power of 2, which equals to, well, 20 divided by 4, which equals to 5. So again, you have an odd power. So this is 2r, 2 to the 2, equals 2 to the, 2RL, just write this whole thing. 2RL equals to 2 to the 2 times by 5, like that. Again, odd. And then lastly, just do one more where I is equal to 8. Well, then in this case, 8 divided by 2 to the 3. This just equals to, well, 8 over 8, this equals to 1. So in other words, this, if you write this as 2RL, and the highest factor is, again, 2 to the 3, this equals 2 to the 3 times it by 1, where, again, this is odd. Alright, so now let's take the look at the scenario where r is less than k. And again, I is even, and we're going to have, let's say, this r is less than k. So what we'll get is, then we're going to have I is equal to 2 to the RL, and put that inside our big equation on the left side was, this is summation up to n. This I equals to 1 of, this was m2k over I, like this. So going back up here, so m over 2k, no, m times 2k divided by I. And again, we're not summing it up now, so we'll just ignore this. So just leave it like this. So I is equal to that, and then we're going to throw that inside. So let's throw this inside. This becomes m over, or m2k over 2RL, 2RL. And now these ones we could subtract the powers and move those in front. So this becomes 2k minus r times it by m over L, like that. And now this is also going to be even. And this is because, well, this right here, because r is less than k, so r is less than k and k is greater than or equal to 1. Yeah, so then this right here is going to be greater than 2 to the 1. Or greater than or equal to 2 to the 1. So in other words, this factor is always going to be even. So this is going to be even. And then this right here is going to be odd over odd, and they're both integers. And this L is included in M because M is every single one. So for example, this 5 right here, and this L is less than I. So then for M will have, actually we'll do this one instead. So in this case, M is going to be M, or let's go M over L equals to 1 times 3 times 5 times 7 times 9 divided by 5. So in other words, these cancel out. So it's going to be an integer. Equals odd integer. Or even, don't even need to write odd integers, just write integer. Like that. Well, or actually just for completeness, let's write odd integer. So yeah, so that's going to be odd, and there's going to be integers, and that's even. And yeah, so it's odd over odd, and it's an odd integer because they cancel out. Yeah, and I'll just put in brackets M contains L. Contains L, and they cancel. Yeah, let's do this. M contains L. Alright, so now the last one to check. So basically this is saying all the terms are M, so M times 2k divided by I is even when I is odd. It's even when I is even, and R is less than k. So this is even. But now let's check when R equals to k. Then if we have this, then L has to equal 1 since, and we'll write if it's not equal to 1. Let's say if L is greater than 1. That means that, well, L is going to be greater than or equal to 2, but we know it's supposed to be odd, so, but anyways, let's just say it's greater than or equal to 2. If it's greater than, yeah, if it's greater than 1. So if it's greater than 1, in other words, not equal to 2, then, yeah, then we'll have I, which equals to 2, RL equals to, yeah, which equals to 2 KL, because they equal, because R equals to K. Then this is going to be greater than or equal to 2k times 2 to the power of 1. Or that's just L is 2. In other words, this equals to 2k plus 1. But we can't have this because, yeah, we can't have this because, well, but 2k is the largest power. Largest power of, I'll just say largest power of 2. Power of 2 less than or equal to n. Yeah, so then basically what this means is that I is greater than it's greater than n, because this is already the one less than, biggest it can be is n, and now it's saying I is greater than n, but we can't have this because we're summing up to n. So thus if r equals to k, then L equals to 1, and we get I equals to 2, RL is equal to 2K, and L is 1. Yeah, this one is L is equal to 1, like that. So basically, this equals to 1, equals to I. Let's put that like this. And we already saw this scenario here. That's when we were just showing that L is odd. So if I is equal to 8, yeah, for example, then we have this one, L is equal to 1. So for example, I'll just go for example. And it's basically when when it equals to when 2k equals to n. For example, we'll go with for n equals to 8, then 2k, the largest power, is going to be 2 to the 3. Yeah, so 2k equals 2 to the 3. 2k equals 2 to the 3. It's the largest power. And this is also the largest power. Yeah, this is also equals to, yeah, this is just equals to 8. And this equals to our 2RL that we had, which is 2 to the power of 3 times 1, where this is L. and 2 to 3 is the highest power. So that's exactly this part right here. So yeah, that's pretty interesting stuff. So yeah, so basically let's put this all together. Thus, for r equals to k, then if we look at that term, for r equals to k, we have that term m 2k over I equals to, well, that just equals to 2k. So equals m 2k over 2k. These cancel. This equals to m, which is a sum of odd is a product of odd integers. This is equals to an odd integer. Yeah, so putting this all together, this means that m times 2 to the power of k divided by I is an even integer for every I, because remember we had it even over here for r is less than k, and this is where I is even number, but r is less than k. And it's even here when I is odd. But when I is even and equals to 2 to the power of k, that is when, well, I mean, that's when r equals to k. Then it's an odd integer. So when I is equal to 2k. This means that m times 2 to the power of k times Sn is an odd integer. And this concludes our proof. Basically, for example, what this means is if you have an even number, even plus odd equals odd. So that's the key thing to realize. For example, 2 plus 1 equals 3. 2 plus, or we can even just pick any random one. Let's go to 12 plus 3. That equals 15. So in other words, you're adding an odd amount of numbers to it. So it's always going to be that. And basically put this all together, we have, thus, I'll just, in summary, I'll just put it in summary, because we already had our proof, this concludes our proof or thus statement. Thus, or in summary, we have, put this as a U, and this what we have in summary, m 2ksn is not equal to m 2km because this is odd while this is even. And this basically means that Sn is not equal to m, so Sn is not an integer. Not an integer. Write it here. And yeah, this is pretty much all we have for today. I'm just going to box this in, and we are done this epic long video.